Thanks for reminding me. Okay. All right. So we have this molecule here, um, clami, clomipramine. I guess it's some drug called anafranil. It's used for OCD apparently. Um, so it's asking which of the two nitrogens here, right, are more basic. So if you do get a question in terms of basicity, right, let's say you got a bunch of amines to compare, essentially what you're trying to do is it's kind of like Aryl factors again, except really it's the RIO part, right? Because if it's all amines, right, the atom's going to be the same, right? So what kind of, the way you could qualitatively do this is what is kind of delocalizing lone pairs, right? We kind of did this when we got to aromaticity, right? When we, oh, whoops, that's white. So let's change the color here. So let's put a lone pair here and we'll put a lone pair here, right? And really remember how good a base is basically how localized its lone pair are, right? So in this case, let's look at this top one, right? We have this lone pair. It is conjugated with this pi bond, right? Can just go around the ring there, or it could conjugate with the other pi bond, right? Here we have 1, 2, 3 alkyl groups, right? So which one of these is more localized? Madrona says the one in the ring. Everyone agree, disagree?
No, I'm saying the one in the ring is not localized. The one in the that's like the one that's separate on its own, the lower
Yeah, okay.
one, is the one that's localized.
Right. So the one outside, right, this bottom one, this aliphatic kind of nitrogen, right, is all connected to alkyl groups, right? All it has is 3 alkyl groups. If anything, this is very basic, right? So this is another kind of thing you could think about is more alkyl groups you have, right? Kind of similar to a carbocation, right? Via hyperconjugation, it's going to be pushing more and more electron density towards nitrogen, right? So that's a very localized lone pair. Therefore, is it more basic or less basic? More basic, right? So amine basicity is not too bad, right? Just remember, like a lot of people don't try to protonate it or deprotonate something, right? When you're kind of looking for basicity, right? Because you've probably done a lot of acidity question. For basicity, you look at the molecule as is, right? You don't have to like change it, right? We could just apply Aryl factors directly. Okay, now I'll give you guys 2 different ones. Molecules here. And compare those ones as well. Just paste them all up in here. It's one. You guys a minute to do both of these questions. And oh, that's a nice one here. Surprised they have it in this textbook. I'm not going to put the name on that one, but okay. So I'll give you guys a minute. So actually, let me label them too. So when we discuss it, we could refer to them more easily, right? A, B, C. And what is this? We'll call this D, E, and F. So in each molecule, we'll, look at the molecule and then kind of determine which one of these nitrogens is the most basic and what, like your reasoning for that. So give you guys a minute to do that. Okay, so for the first one on the left, right, which one is the most basic?
C.
C, right? You could just type it in the chat. Um, right, so all of these, right, let's kind of, this one, so B we could knock off right off the bat, right? Because that one has actual delocalization, right? Just to make it clear, right, it's conjugated with this pi bond from the carbonyl, right? C and A actually both have localized lone pairs, right? So here you have your lone pair, right? And then here you have your lone pair. But how come C is more basic than A, even though they're both localized? B is going to be the least, actually, Madrona. It really comes down to, well, it's not really about donating the ring. Think about the hybridization in each of these, right? This is kind of the last thing of Oreo, right? RIO, right? Orbitals, right? It's sp3 versus sp2. And what do we know about orbitals in terms of their distance from the nucleus, or S character, actually? I should talk about S character is better. Which one has more S character, sp3 or sp2? sp2, right? If it has more S character, right, it means it's more similar to or closer to the nucleus because it resembles more of an S orbital, right? If it's closer to the nucleus, that lone pair is a lot more stabilized, which means it would be harder to act as a base, right? Because it's being stabilized by a positive nucleus, right? So that would be a reasoning specifically why C is the most basic over A, right? It's not just because it's purely, alkyl, right? It's, they are both localized, right? Just one is more stabilized than the other. This one has no stabilization, C, because it's sp3. It's a bit further from the nucleus. All alkyl groups here, you're in an sp2 orbital, right? It's a lot closer to the nitrogen nucleus, and therefore it's more stabilized, right? So that would be a reasoning if you were asked a question, right? Because usually he's, this question asks just what's the most basic or whatever, but like generally both Professor Biscoe and Boson, they would want to see your reasoning, right? So you can't you gotta make sure your reasoning is solid so you can, get max credit. Okay, how about this one here? Does anyone know what this is? I mean, well, not anyone. If you looked at the book, you probably know what it is. But which one? So someone says I. Does everyone agree? Oh, yes. Sorry. Yeah, that is an E. Even I forgot I wrote E there. Yeah, that's an E. Uh, no, sorry. I look like an I to me to my handwriting so bad sometimes. But yeah, it's E, right? So D and F both have conjugation with the pi bond right next to them, right here and here. So you could say they're delocalized lone pairs, whereas the one here in this kind of six-membered ring here, right, it's locked in on the nitrogen, right? There's all alkyl groups next to it, so it's localized there, and it's going to be extremely basic, right? So yeah, this is LSD, right? If you remove this, so this is lysergic acid, lysergic, I think it's lysergic acid diethylamine, or lysergic diethylamine. But basically, what its predecessor is, right, is if you remove this group right here and make that an OH, right, that's lysergic acid. And that's naturally found in, I believe, the seeds of a wheat plant or something like that. So you extract that, you do a coupling. I shouldn't tell y'all how to make LSD, but yeah, that's the natural kind of molecule you can use to synthesize this final amine, right? And this is a very psychoactive substance, right? That when it interacts with your body, it gives you, all sorts of different effects, usually ranging from hallucinations to, visual changes or perceptory changes, stuff like that. Yep. Um, cool molecule there, LSD. Okay, let's move on to some reaction questions. Let's see which one of these are good here. Okay, let's do 22. Sorry, what? Like least basic. Yeah, I would put that as the least. Yeah, I'd put that at least basic because first it's tertiary, and then the withdrawing group, right, is technically you have two withdrawing groups, but I guess the carbonyl should be stronger than both the pi bonds that are next to the F. Yeah. Yeah, that's the main thing is F can conjugate both ways. Yeah, I wouldn't. I'd probably say D, but I mean the question asks what's the most basic. But if you did have to rank them, probably D last, just because the carbonyl is probably more electron withdrawing than the other two groups that are attached to F. But yeah, maybe you have to experimentally see that. Yeah.
So my reasoning is the most basic is the one that's least acidic, and vice versa.
And you don't really have to use that reasoning for basicity questions. You just have to just talk about the lone pair and its localization and any stabilizing factor, right? So
Okay.
like, yeah, try not to mention acidity because you're not really talking about acidity. When we talk about acidity, then we use basicity because we always use basicity to talk about acidity, right? But when you're talking about basicity, you don't have to mention anything else. You could just analyze it as is, right? Because remember, Aryl is based off the conjugate base, right? In this case, we already have bases, so we could just analyze them as is, right?
Thank you.
Okay, all right, let's see which one. 22.49 looks good. I think that's reductive amination. We draw that out then, and we'll work on the mechanism here. Okay. So here, let's do this one. We have formaldehyde. Let's change colors. And technically we have NH3, and then we have H plus, and I think it's sodium cyanoborohydride. That's what it's called. I feel like that's what it's called. And then out of that, you just get a simple methylamine, right? So CH3 and H2, right? So as I mentioned, right, this is I guess example of technically reductive amination, right? Basically, you're forming an imine, right? And then you treat it with a reducing agent, right? Sodium cyanoborohydride, right? And you can get a full-on amine. Basically, it reduces the C double N bond, right? So I believe the reason you use this cyanoborohydride, it's very selective towards these amines as opposed to any carbonyls. So if you ever see that, you could automatically think you're about to go for making some sort of imine out of a carbonyl, basically, right? All it really is if you think about it, right? How can I draw this in a more general way, right? So you have your carbonyl here, right? And let's say this is R and R1, and this is R2, right? You have any sort of amine here. I think the book might have a general way to describe it, but R1, R2, and then we'll make an amine. let's just do a primary amine first, right? So we'll call this R3, NH2, then you put it under these conditions, right? The final product, right? Let's say this was a quick way to kind of think about the final outcome. We'll do the mechanism right after this, but is your nitrogen, right? Is essentially, so this bond here, right, is going to be our carbon nitrogen bond. So that's that, right? Attached to it are R1 and R2, right? So essentially we replace this carbonyl with this bond between this carbon here, right, and our nitrogen from our amine. And then that's attached to any other R groups it might have, right? So here, well, no, we'll just keep it white here. So then it'll just be R3, right? So R's could be H's, right? What else can R be? Any alkyl groups, probably phenyl groups, stuff like that, right? Any ketone it works with, or aldehyde, any of those, right? So here, the only thing is our R groups, right, are what's it called? H's, right? Oh yeah, I forgot the H. Thank you. Here, right, really, if you think about this, is that this is our carbon, right, which is here, right? There was two H's. So if I drew this like C, N, right, NH2. So when we have ammonia, we just lost one proton. So that's where the NH2 is coming from, right? Our R groups technically on the nitrogen are just two H's, right? And then we have one R group is an H, one R group is an H, and what the borohydride does is add that other H, right? Remember here, there's well, we don't show, but there's an H here too, right? So that's where that CH3 is coming from, right? So it looks a little tricky, but honestly, this is one of the easiest reactions to get the product from. All you're essentially doing is replacing the C-double-O bond with the CN bond, right? And this can only work for like ammonia, primary and secondary amines. So all you have to do is just remove one proton off your amine, and then you get your final product. So now in terms of the mechanism, it should be similar to what we learned in what was it? I think it was a chapter 18. Which one was the one with no, it was chapter 19, right? With amines and all that stuff. The purpose of the cyanoborohydride, right, is it's a selective reducing agent, right? So you have a lot of reducing agents that we've seen already, LAH, like the lithium alumina, like the terbutoxide ones, right? That like worked on like carboxylic acid derivatives. We used regular borohydride, but like the whole point is, and this is kind of one of like the important things in organic synthesis, which you see a lot of good groups kind of focus on. It's all about selectivity. Anyone can do any reaction at this point in time, right? There's enough stuff out there, research, that you could more or less create everything with enough steps, right? What separates like kind of good chemistry from great chemistry is being selective, right? So this specific one is very selective, that it only works with amines, right? So when you react this with any sort of amine, you form an imine, right? And then that borohydride, like let's say you had another carbonyl or something else on the molecule, it won't reduce those, right? So you could have basically very selective formations of like amines on, you want to functionize one carbonyl on your molecule to an amine, you can do that, right? That's kind of the purpose of it, right? Is that it prevents like you from doing, creating undesired alcohol groups, really, if you think about it. Okay, so let's start with the mechanism. It should just be pretty simple. I'm gonna protonate this first. I like it. I like doing it that way. I just hate creating the negative charges. That's really what it is. Where are we? Aryl. Okay. H and H. Right, now we could have our ammonia attack us, or attack the molecule, not us. Right, that's gonna do here. That's gonna kick this up. And now we have our first intermediate. Does everyone remember what this kind of intermediate is called? You have the OH in the amine attacked here, right? This was called a carbonyl amine, right? One of the intermediates in our amine reactions, right? Now he said he's cool with that intramolecular proton transfers. I'm gonna go ahead and just do that. All right, he does the wiggly H, right? Whatever. So this is now OH2 plus, this is now H2 here. Still have our H's and H's. You don't have to show the H's. It's just in this case, it's a little easier to keep track of them, right? So now we form our amine, right? Kick off water, right? Let's go down this way. Now, the only difference here, right, is because we have this reducing agent, right? Instead of deprotonating, right, at this point when you have this protonated amine, right, it's very selective towards reducing this species, basically, right? And this is where the borohydride comes in, right? I don't know if he represents that H minus. I'll just draw out the full structure just to be safe. Maybe I'll just have to draw it out. Just trying to be a little lazy here. I'll just draw it out. It's fine. Then we should technically have minus and a plus here, right? Why would it still have a positive charge? Okay, so let's explain, right? Let's start from this one here. Neutral ammonia comes in, attacks this, right? Oxygen gains a lone pair of electron, right? Oxygen is now neutral. Ammonia got a positive charge. Intermolecular proton transfer. Essentially, all that happens is this proton moves to the OH group. There's a positive charge here. Neutral ammonia, right, as Mohammed said there, right, is now donating a lone pair to form an imine, right? Therefore, if it's giving up a lone pair, it's gaining a formal charge. This is being kicked off the molecule, right? So the charge doesn't change on the carbon, but nitrogen is now sharing electrons, right? Before it had both of these two, now it technically only has one, right? Therefore, it gained a formal charge there. And that's how you get your protonated version here, right? Does that clear it up? Just follow the charges, right? Are we good here? Can I continue? Okay, cool. All right, so now next thing, right? Usually remember at this step, what happens is like a base or water or something comes in and just deprotonates it and you get your final amine, right? But the only difference here now, right? Similar to LAH and borohydride, right? Remember these are all kind of delivery agents of H minus, right? So the way we always draw these things is basically, what is it? Right, it comes from the bond between boron and hydrogen, right? Because the whole point is the reason why this is a nucleophile is because there's some sort of polarizability between the boron and hydrogen, right? And this electron withdrawing groups helps a little bit with that, right? So you always draw it like if you want to draw out the full structure. That's why I'm not sure if he accepts like H minus. Probably wants you to draw it like this if you're asked for a mechanism, right? And then this kicks up, and boom, you get your final product, which is now a methylamine. Oops. Now it's this. So this is NH. Right? C, H3, and H2. Right? That's our final desired product. All right. What's your question, Madrona?
I'm just gonna use my mic. Yeah, so the one that you just drew with the green color, the product.
Mm-hmm.
So there's two R groups on the C and
Mm-hmm.
one R group on the N. So the original molecule only had the R1 and R2. So the third R came from the R3 NH2 on top of the arrow. Is that it?
No, there's no third R group. It's hydrogen that was added here, right? So you meant this R3 here?
Yeah, the other one on the product too.
Like here?
Yes.
That's already attached to nitrogen.
Okay.
Yeah. So like if you had, in this case, in that R group is, right, in this specific example, that R group is H, right?
Okay.
So anything else, it would be like methyl, ethyl, etc. Right? That was just trying to give you a generalized example, right? The H specifically comes from, let's make this orange, right? So this H comes from the borohydride, right? So this is where really everything in this molecule comes from, right? The nitrogen, the NR part comes from your original amine or ammonia, whatever you have. The extra H here comes from your borohydride, right? And the R groups and carbon are all from the original carbonyl. This is reductive amination.
Okay, thank you.
To answer Nada's question there. Okay, okay, let's keep going down the list. Shoot, I forgot what problem this even was. Which one was this one? This was 49. Just put that here. Okay, let me go back to the syllabus, see what other questions he had there. 49. Okay, let's see at the other ones. 50. 51. Okay, let's do 54 then. Actually, I'll let you guys attempt that because it's a synthesis question, so I don't want to just work it out completely for you. I'll let you guys try it a little on your own first. Okay, let's see which one we want to do here. Let's do A. That should be pretty easy. So you're starting off with benzene, right? And you are making it's like an acylated methamphetamine, basically. That's funny. It's just a few atoms away from being meth. Yep. Okay. I should say amphetamine, which is Adderall. Okay, right. So I guess I'll give you a little bit of hint, right? This shouldn't have to use Aryl diazonium. I don't think so. So you don't have to really worry about trying one of those reactions. Should be able to do it without it, I think. Okay, so yeah, I'll give you guys a few minutes to try that. Okay, let's go over this. All right, so actually, I guess I lied. You could do this with aryl diazoniums because I was trying to figure out a way. I was looking at what the book did, but I like the way I kind of did it too. But you could always look over at the way the book did it too. But maybe if you had something different too, we could, after I go over how I wanted to do it, we could go over that too. Okay, so first things first is see what changed in the carbon skeleton, right? We have basically this giant group attached, right? Benzene is as it is right now, right? So we have to add a carbon and a nitrogen. So really, we know basically at some point we need to get an intermediate, right? That is going to look like, this is kind of how I always worked with the retrosynthesis is, I don't know what's going to be between this and this, but I know at some point I need to create this, right? Because with this, right, with this functionalization, I can do a lot of stuff. I can acylate it, I can methylate it, right? So if I somehow get this out of my benzene ring, we're kind of, at a good position to go forward, right? Um, yeah, so you could do a couple of things. I think the book did a Friedel-Crafts alkylation, right? You're gonna have to, like, the first thing you should notice, right off the bat is you need to do an aromatic reaction here, right? One of those electrophilic aromatic substitutions, right? What I did, or what I wanted to do, right, is I was originally gonna brominate the ring, and then I realized instead of that, we can just what's it called? Create one of those Aryl diazonium salts, right? So the first thing I did, what's it? Sodium nitrite, and then an H plus, right? I think I don't know what source of acid it uses. I think it's an HX. It should be HX. HCl. Okay. Technically, you could use any yellow acid, but we'll put HCl for consistency's sake. So anyways, right, we could do that, right? This is going to create an intermediate that looks like this. I guess for this, right? This is a very good intermediate, right? Mainly because when this reacts with something, right, you're going to get nitrogen gas as a leaving group. And nitrogen gas is probably the best leaving group in all of organic chemistry besides like other gases really, right? But it's something that's always wanted to exit the molecule, right? So that's quite a reactive species we have here, right? So now what I did next is one of the Sandmeyer reactions, right? Specifically, right, I need a carbon here and a nitrogen here, right? So I can turn this into a nitrile, right? So if you do copper CN, right? So this is one of those Sandmeyer reactions. Remember, if you use copper salts, copper bromide, chloride, iodide, and I think cyanide, there's probably a few more. Can't remember them. Those all react with the Aryl diazonium salts, and you can basically get a direct halogen, like it's an alternative way to halogenate a ring, right? Or you could, make a benzene nitrile or whatever, right? So now here, right, after treating this with copper cyanide, we are going to get a species that look like this. Now, it's a triple bond, right? We are one step from going from this to this. Now, does anyone know how do you get from a nitrile to an amine? Yep, right. So it is just what's it called? Right. So if you have LAH, you know what? Let's write it out. LiAlH4. Followed by any sort of workup. Let's use H2O, right? What that does is reduce all of these carbon nitrogen bonds, and it reduces the amines by, protonating them, right? And then you have your amine, and then I think you have a deprotonated amine, or like N minus or whatever, because of the LAH conditions, and then the water is just to work it up to finally NH2. So essentially, this is the bond, right? This is the C here. So let's maybe make this red, right? This C is this C here, right? So we are reducing that C triple N bond into CnH2, right? This is just this is from, I think, chapter 20, right? Okay. And now we can do a couple of different things here, right? One is You could I think if you just hydrolyze it completely with any acid source, that should work too, I'm pretty sure, for nitriles. I think that might make a carboxylic acid. I'm not sure actually. I forget. It will? Okay. Yeah. I don't remember because it kind of oxidates it. Okay, right. So now we're at this molecule, right, that I told you, right? Now we could do all sorts of different reactions to basically get what we want here, right? We can just, if we really wanted to, right, we could just go ahead and directly acylate this, right? But it's better to install that methyl group first. Now, there's two ways we could technically install methyl group. One is just simple alkylation of your amine, right? So if you just use any what is it? Methyl iodide or something like that, right? So we could, and the thing is, I think on Bisco's exam he'll accept this if you did this, but the reason I could understand why the book did this a certain way too, right? Is technically you could use what is it? Something like CH3I, right? Methyl iodide, right? And that's going to react with your amine there, and you're going to get this. And maybe just to be very specific, if you wanted to do it this way, you could use one equivalent, right? And that'd be perfectly okay, right? Because I think he's fine with, as long as it creates the product, right? It's not really about being efficient. It's more about knowing that the chemistry works. So this is going to be methyl, this could be H, right? This is a benzene ring. It's not going to react directly with the benzene ring. If you're talking about the methyl iodide, yeah. Plus, yeah, no, it's not going to break aromaticity there. So you're not going to. That's why you need like a Lewis acid and stuff in a lot of those electrophilic aromatic reactions, right? Yeah, I mean, if you wanted to, you could have made a carboxylic acid. Like I said, there's a lot of ways you could get this, right? You could have made a carboxylic acid, right? And reduced it, made it into an amide, right? So if you basically made benzaldehyde, or no, benzoic acid, sorry, right? Then turn this into the amide, and then reduce that amide into the amine, right? That's another way. Like I said, there's a lot of ways to get that first amine, but I said the main thing we're looking for, you have to get that. That, in my opinion, in this whole synthesis is the key intermediate, is getting this, because this is where we can do all sorts of reactions to get our final product, right? So at some way you have to, that's why I like working forwards and backwards for synthesis questions, right? Is, try to figure out something, one intermediate in between, and that's usually enough to get you started, right? And this was the main one here, right? So yeah, we methylate it here. Yeah, so that's the point I was getting at, Ali, right? That's why I wrote one equivalent here. And I was mentioning I wouldn't really want to do this, but this is a way you could do this, right? Is the whole issue with alkylation, right, is it's kind of like a chain reaction, right? Is when you alkylate it once, this makes this amine even more basic and more nucleophilic. I wouldn't say too much nucleophilic. I guess it's more nucleophilic, but really it's just gonna keep basically alkylating, right? Then you'll get another methyl, and then you get your quaternary ammonium salt, right? So you get this, like something like that, right? So that's called exhaustive alkylation. I believe that's what it's called, right? But I think if you do it like this, it's fine. The better way of doing this, right, is what we did earlier, right? This is one of the best ways to create like a methylamine, right? Just using formaldehyde and doing a thing. So alternative, I'll write here, right? And this is better. Technically, I think on your exam, both will be acceptable, right? As long as you write one equivalent or whatever. The alternative was what we literally did above, right? If we use formaldehyde, because essentially, right, this is going to turn into CH3, right? Right. So that's why this kind of, if you manipulate the carbon part of your carbonyl, you could install any R group you want on an amine, right? So formaldehyde will always install methyl on your amine, right? And then what do you need? You need H plus and sodium borohydride, right? That would be the better way to methylate this, right? Using this conditions, right? Either one leads to the same methylated amine here, right? You know, this one is easy to remember. This bottom one, the reductive amination, is better, right? Because it's more controlled, right? You're only gonna get this, right? The issue with the first one is even if you did a good molar equivalence here, you're still gonna get some, you know, secondary or quaternary byproducts, or I should say tertiary and quaternary byproducts, right? And then the last step is pretty easy, right? If you treat this whole part, right, or really not treat this, you could treat this as a giant amine, right? How do we make amides, right? We could just use a carboxylic acid derivative, right? So acyl chloride, acetic anhydride, right? All of those should be fine to, what's it called? Do it. We'll just use the chloride because that one's easy. So what do we have? Methyl here. So we have methyl and then Cl, right? And boom, you have your final synthesis, right? So I think the way the book did it was they started off with an alkylation, then did a radical reaction and did that. So there's a lot of different ways you could always do these questions because at this point in the course, you have a lot of different reactions, right? To get from one place to another, right? So it's just really the toolbox. That's how I like to think of it, or that's how I was taught it, right? Like all the reactions are tools in your toolbox. Okay. Let's see what else. After 22, keep going down the list here. Oh, that's cool, actually. I don't know if this was on your review problem. Oh, no, he skipped that one. Okay, never mind. Okay, let me see. All right, there we go. Let's do 57. I'll actually post these here. And give you guys a few minutes to do it. So it's just predict major products from a series of these reactions. The B and C. Okay. Oh, damn, I kind of cropped that one bad. Oh, well, that's fine. Just ignore the bottom text. Okay, so take a few minutes to do these. So basically all it's asking is that's your starting material. You are going to treat it with, 1, 2, 3, and then, what's your final product after that? Same thing for the next one is you start off with that, you treat it with 1, 2, 3, and 4, and then what do you get at the end, right? So just take 2 minutes maybe to do that. Oh, my bad. I wasn't thing. Oh yeah, no, I was showing from the old thing last semester, I guess. This was an example of Gabriel synthesis. But I thought I had the full mechanism drawn out once, but you guys probably have your notes anyways. But I mean, this question's not asking mechanisms to begin with, so that's fine. What is it? So this one, what I was saying, does anyone remember what this was called? This nitrogen molecule here. But anyways, first step, right, is just base, right? You have a very acidic proton here. You have a base, just deprotonates it. So technically, after step one, this is all you really get, right? And then you have ethyl bromide, right? You have a nucleophile now. You have an electrophile, right? So after step two, all you're really doing is alkylating it. Okay, and then we have ethyl, so it would be that. So this would be N-ethyl phthalimide, right? So that this one, the species right here is called phthalimide, right? And then this would be N-ethyl phthalimide technically, because the N part represents the R group on your nitrogen there. And then second step, right, is essentially just like a hydrazone reaction, right? And it replaces this CN bond, right? It basically liberates this nitrogen, this entire group here out of the phthalimide, right? And then you actually replace it with two nitrogens here. You could actually do the second step. There's another, like instead of using, what is it, hydrazine or whatever, what else could you use instead of hydrazine? To get your final product, right? So yeah, you could also, because these are carbonyls, right? If you do acidic workup, you could essentially turn them into carboxylic acid groups, and that would also release the amine, right? I mean, you could kind of think this as a diamide or something like that, and essentially you're releasing that nitrogen group off the amide. The only difference with that, right, is um, technically you have an amine in acidic conditions, so I think you'll actually get like a protonated amine. So you'd have to do one more step actually, right? Which would be to deprotonate it. But here, after third step, right, we get our final product, which is going to be this, and technically a byproduct that looks like that. Actually, it should have H's here if I recall. Yep. So the main product you're looking for is the ethylamine, though, right? That's the whole point of this Gabriel synthesis, is essentially phthalimide is kind of like a docking station to create your amine, right? It's a source of nitrogen, really. It's a really very cool way of doing it. So no, I'm not showing a mechanism. So let's go on to C, right? Okay, so we have alkyl bromide with NaCN DMSO, right? You see strong nucleophile, you see a polar aprotic solvent, right? What kind of reaction is the first one? In terms, it's a general type of reaction. Strong nucleophile, secondary alkyl halide, polar aprotic solvent, right? Orgo 1 stuff. What do we call this reaction? Which someone literally mentioned in the chat too before. It's N2, right? It's kind of clear giveaway with the solvent too, right? So simple first step is literally just replacing bromine with your CN, right? That's it, right? Second step, someone mentioned before, right, is we have, what's it called? Your nitrile, maybe I'll draw out the triple bond here, right? And we are hydrolyzing it with heat, right? So it turns a nitrile into what functional group? Carboxylic acid, right? So let's keep moving forward then. Oh, I don't know why I started adding so that carbon here is now the carbon in the carboxylic acid, right? So we still have the same amount of carbons, right? Step 3, SOCl2, carboxylic acid. Which derivative are we creating here? Acyl chloride, right? So when you react thionyl chloride with your carboxylic acids, you turn it into a very reactive acyl chloride, right? And then acyl chloride with any sort of amine, right? So like ammonia or any amine turns it into an amide, right? Which is our final product, right? NH2. Pretty straightforward there. Okay, let's take a break here. Let me start, probably resume at 120 because I want to go find those peptide problems. Probably maybe do 1 or 2 more problems here. I gotta see which ones I didn't cover. But I think most of the stuff we did here, we did the reductive stuff, we did a bunch of synthesis, talked about basicity questions. Otherwise, we'll probably just practice peptide questions then. And that'll probably be covering it for all. Did you guys finish the carbohydrates chapter? The last step? Oh, sorry. I don't know why I wrote 4 again. So are you from step 3 to 4 or 2 to 3? Do you mean 3 to 4, right? So 3 to 4 is just the simple amination of your amide formation or amination, however you want to look at it, right? So remember when you have any sort of carboxylic acid derivative, if you react it with ammonia, a primary amine, right, or a secondary amine, right? Any one of these, right? Essentially, these are nucleophiles, right? They're going to attack here, here, right? Kick off the Cl, right? Get deprotonated, and you get some sort of amide. And then the R group determines what R groups are in the M, right? Okay, yeah, let me go find those problems then. I think Professor India has some exams like that. Let's go find out. Actually, I don't know if I still have those. Damn. Okay, let me search a bunch of my folders on the computer. But yeah, we have a break until like 120-ish or whatever, or whenever you hear me talk again. found one of those peptide questions, but let's do 2 more amine questions and then we should be done because 70 and 71 will do. Mostly because it's one more mechanism and another quaternary ammonium salt, which we didn't really, kind of briefly did. But okay, let's push this. Okay, when the following compound is treated with excess methyl iodide, quaternary ammonium salt is obtained that bears only one positive charge. Draw the structure of this quaternary ammonium salt, right? So this is kind of a dual question, right? Let's see, let me put my laptop on charge. But it's the first part of this question is which one of these amines, right, is more basic or kind of more nucleophilic, right? So the one on the ring or the one all the way at the end of that carbon chain, or I should say the one next to the ring and one at the end of the chain, right? So Drona and Nada, I would assume hopefully most people agree with them, right? It's what we did above, right? Then the one next to the ring, right? Oh, it on white. Yeah. Give me 1 second. Let me just battery things, battery saver off. 1 second, guys. Let me just. Hopefully this doesn't mess up. Okay, cool. It's on 120. Turn that off next time. There we go. All right. So yeah, this delocalizes with the ring here, or I should say, should not go like that. It should go like this, and boom, right? Then it'll delocalize there. Here we have a very good localized lone pair. So we did the reaction here, right? Why true arrow like that, right? And then this would essentially happen 3 times, right? It would happen once, right? Methylates once, then it would methylate again, right? So our final structure, right, is essentially we're just going to redraw all of this, but now and how many methyl groups are going to be on this nitrogen? For the final structure of the quaternary ammonium salt, not after this one reaction. Sorry to be clear. 3, right? Because if it's a quaternary ammonium salt, it must have 4 alkyl groups, which means the other 3, obviously this gigantic chain is 1. So you have 1, 2, 3. Don't forget the positive charge, right? Because it doesn't have a proton anymore. It has all 3 alkyl groups, or 4 alkyl groups technically, right? So that'll be your final product. Okay, 22.71. I was gonna actually start the peptide stuff, but then I saw this problem and I was like, this feels like a problem you might end up picking. Or if anything, even though it's a good mechanism problem, I saw it and I thought it was pretty good. So let me actually if this does end up being on the exam, no one can complain about it. I mean, I think it's pretty fair how he's putting the exams. I mean, I think the last exam, a lot of the questions were directly from the textbook. So, if you do the practice, right, should be no reason to not do well. Okay. So draw a mechanism for the following transformation, right? So we have pyrrole here. Oops. Pyrrole, pyridine, acetyl chloride, and we formed a 2-substituted pyrrole. We protonated our, excuse me. We protonated our, what's it called? Pyridine, right? Okay, so essentially what we really did was we formed a bond between the carbon here and the carbon in the acid chloride, acetyl chloride, right? So this is gonna kind of actually start off like what kind of reaction is this similar to from chapter 18? Oh, do you guys want to try it on your own first? I should have asked that before. Yeah, okay. So I'll give you guys a few minutes to try it on your own, right? But I guess I gave you the hint is it's gonna be, I mean, not really a hint. You could see it's 2-substitution, right? So, and I also said it's similar to an aromatic reaction. Okay, I'll let you guys try it. Okay, let's go over it. If you didn't finish, well, let's follow on or finish up while I'm doing it. Okay, so this is going to basically follow your typical kind of electrophilic aromatic substitution, right? And I think the book explains too why the 2 position is more likely. It's really just one additional resonance structure. It's the same thing with kind of like a para-meta substitution, right? You could kind of consider this position para, right? Sorry, ortho, and this other one meta. So this 2-1 is like ortho, and this one is meta, right? So when you do an attack from this position, right, or a substitution on that position, you will see that we get like 3 Yeah, it should be 3 structures. The other one should get 2 structures, right? And that's why pyrrole specifically is a good nucleophile to have 2 substituted kind of products formed from it. And actually, I mean, I'll show you another product that you guys have probably seen in real life or used. Hopefully you didn't use it, but it's another kind of 2 substituted pyrrole product. So anyways, let's start it off. Let's use orange. I haven't used orange all day. Oops. Okay, so we have our acyl chloride. Pink arrow here. Kicks off, right? What's this kind of similar to that we did in chapter 18? So an acyl group, we are acylating this thing, right? What was that called again? Yep, the Frieda-Crafts acylation. It's literally that, but only difference is, well, it's still technically that mechanism, right? It's just the difference is instead of a benzene ring, right, we still have an aromatic ring here, right? Pyrrole is aromatic, right? It's at the difference is that it's a 5-member nitrogen ring, right? Because this lone pair here, right, you have 6 pi electrons, right? Same exact mechanism though. Then you have Cl here, you have your methyl here. We broke that open. Should have a positive charge. So broke this open. Positive charge should be here next to that. Yep. Okay. All right. And I think I'll just draw all the resonance structures. I mean, the thing is, yeah, I'll just draw them for the sake of drawing them. Because it's kind of the same thing with the sigma complexes is what I was thinking about. I don't know if he does or the book does on for this question if they draw out all the resonance structures, but yeah, it's probably better to just show them. Okay, anyways, this reforms the carbonyl, and then this should get kicked off. It doesn't really matter when that gets kicked off. I'm missing a nitrogen H here. Okay. Next structure is simply just now your actually acylated product here. It's a nitrogen. Plus, you have just your simple group here. You have this, right? And this will essentially delocalize around the ring. I guess I'll just show it here. And oops, why I keep switching to white. On here, this acylated thing here, right? It's kind of like that sigma complex where you have to draw all 3 of the things, right? Even though technically, right, we could just, remove the proton and reform the pi bond. Which I'm just, whatever, it's fine. So consider this your sigma complex for this kind of mechanism, right? So now you have a a lone pair next to a C plus, right? That's one of those kind of patterns. Same thing, you could form a pi bond here technically, right? And then you should have your third structure here, which should be this. So 3 resonance structures, right? So if you are given a substitution like this, kind of treat it like one of those aromatic substitutions where you have to show all the resonance structures of the sigma complex, right? Now we have all three of our resonance structures, right? And then technically, I'm going to, I want to just use the first one, but whatever. I'll just draw extra arrows. It's fine. Oh, sorry, that shouldn't be a CO. Why did I put a CO? It should just be the methyl. Thank you for pointing that out. Right. Then technically, we are just going to have a deprotonation occur. So should be this one. Yep. Right. You're trying to reform this pi bond. So I guess pyridine. That's why. So remember way back the question here, right? We had pyridine, right? That's the whole function of pyridine here, right? Is it's going to just deprotonate this to get our, basically restore aromaticity here. This is going to grab your hydrogen, right? Your hydrogen is going to form your double bond here, that pushes here, and then this pushes here. And now you get your final product, which is two substituted thing. That. And then you have your protonated, am I missing any hydrogens? You should just have your protonated right? That's what they were looking for. Yeah, technically, yeah, the Cl minus is floating around there. So yeah, we could just put that here. I don't think that's too much of an issue. But yeah, kind of treat this just like a sigma complex, except now instead of a benzene ring, the sigma complex is inside of a pyrrole ring, right? But same thing, we just want to show that delocalization of that positive charge throughout the ring, and then you can go back to your final product. So yeah, that's another just a mechanism practice, right? So what I was talking about in terms of a natural product, because you see pyridine and where is it? Thank you. Did I not put that? Yep, I did not. Thank you for pointing that out. Yeah, plus sign there, right? Conservation of charge. That should be it. Okay. So yeah, no, I was pointing out in terms of a natural product, like when you see pyridine in this, I mean, this actually starts with pyrrhonic acid, and then you have a protonated version or a deprotonated version, I think, of the pyrrole, right? So if you have something that looks like this, right? This is under different conditions, right? But this, so you have double bond here, 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 and it should be meta. So here, and then you have your two substituted. Hold up, make sure I do this right. That should be, yep, that should be the structure, and then a methyl here, right? So this is just kind of, because I saw these two things, this is the natural product. Anyone know what this amine is here? It's one of the most addictive substances. No, it's not meth. Meth is pretty sure that should be meth. That's methamphetamine, right? Let me just actually check that. These are just natural things. Oh no, we're missing one more. Why is it not plugged in? Oh, not charging this whole time. Okay. Sorry, meth is, it's one carbon off. This is meth, right? Super addictive thing, right? If you remove this and make this NH2, right? This is one of the most prescribed medications in America, Adderall, right? And the main difference, this is why it's so funny that Adderall is a legal drug, right? I mean, meth is terrible for you, don't get me wrong, but it's literally all the difference between meth and Adderall is a methylated nitrogen, right? That's it. They're very structurally similar. This right here is nicotine. That's why when I saw this, I immediately thought of that. That's also one of the more root of all evil, root of all fun, the way you want to look at it, right? Why is this not? Oh my God, this was not plugged in this entire time. Damn. Okay, here we go. But yeah, nicotine is you know, cigarettes, vapes, all that. I got some blueberry nicotine right next to me. Nicotine salts, right? That's what they use in vapes, right? It's basically there's like, this is technically free-base nicotine. Then you have the salt forms, right? Yeah, but nitrogen, you're right though. It's a lot of bioactive compounds and pharmaceuticals and drugs that you'll always see some sort of nitrogen, you know, some sort of nitrogen group or nitrogen heterocycles, all of them. Even cocaine, right, has what's called a tropane ring, right? Yeah, it's a tropane-based alkaloid, which is basically like a bicyclic nitrogen ring. Like, it's crazy how many bioactive molecules have nitrogen in them in it. So that's why, like, you know, people say, oh, carbon, hydrogen, oxygen. It's really carbon, hydrogen, oxygen, and nitrogen is the basis for all life. Okay, let's get into peptides. We'll probably spend the rest of this time now on this. Yeah, that's the little tidbit of biochemistry on the side, or medicinal chemistry. However you want to look at it. Let me pull up this problem I found. So I think this is kind of how he will do his problems. This is, it doesn't matter what the problem number is, but basically it asks you to synthesize tripeptide ALE. Now, let me ask you, did he say you have to memorize the structures, right? Like, I mean, you should memorize all 20 amino acids because it's going to be very useful for Biochem 1. But he said not to. He said you could write like stuff like ALA, LUE, and then E is actually funny. It's, I don't know why, who designated E as glutamate, but that's what it is, right? So ALA, LU, glue, right? So this, maybe, I don't know how he'll write it, right? But let's say he told you to make it like this, right? Okay, so how do we start off with this, right? And this is how I like to, what's it called? Do it is, you know, if you don't have to memorize the structure, right? You know, any carboxylic, sorry, not any carboxylic acid, any amino acid, right? The base functional group, right, is your carboxylic acid here, right? And then one at the alpha carbon, you have your NH2, and then you have some R group here, right? Only exception is, I forgot which one is the cyclic one, right? I think it's proline. Yeah, so proline is the only thing difference with proline is it's like that, right? H. But basically, the general structure for amino acids are, you know, NH2 and this. So really what you could think about is that R group, right, is like that main base, right? So every, like, let's say ALA, right, alanine should be a methyl, right? So if this, right, is alanine, right? Right, you could think of this as this part right here is ALA, right? And then it's connected to a carboxylic acid group, right? So you could write that as COOH, or you could draw out the structure. I like drawing out the structure. And then the other group it's attached to is its thing, right? That's the best way to approach these problems to make sure you don't really mess up the synthesis, right? But he said he like you guys learned the basic coupling and all that with like DCC, and so I just want to make sure that this is what you guys were talking about in terms of practice, right? Okay, cool. So we're doing the right kind of problem here. Okay, so this is the best way to represent it without messing stuff up, because then you could, you know, KISS, keep it simple, stupid, right? Literally, all you have to do is just whatever your thing is, right? Just draw the N terminus and draw a C terminus, and then you could just do simple reactions in terms of protection, deprotection, etc. Right? So you have to pick a side here, right? So the one we're trying to synthesize here, right, is, let's see, ALA, LUE, GLU. So left to right, does it go N to C or does it go C to N when we write peptides? N to C, right? So that means essentially here we have NH2, and then here we're gonna have COOH, right? Okay. So yes, the order of how you do this does make a difference, because you need to deprotect an N terminus, like you have to either protect or deprotect the C or N terminus, depending on how you couple it. So let's start off with, I guess let's start off with the left side here. Second, this, I don't think we're gonna really need the structure, but just want to have it pulled up just in case. All right, so the first thing we want to do is basically we want to bond ALA, right, to LEU, right? So what we're bonding is what terminus of ALA to what terminus of LEU, right? So for ALA, what terminus is it going to be? C, right? And then for LEU, it's going to be N, right? So you're always doing the CN bonding, right? That's the whole thing with the DCC, right? That coupling agent, which is actually what you could use to make that LSD we mentioned before. Right, the, what is it, dicyclohexyl diamide or something, carbodiamine, something like that. Right, the whole purpose of that is to couple the carbon to nitrogen, right? So what you have to do is, in terms of the ALA, right, which side are we going to protect, the N terminus or the C terminus? Think about what I asked, right? It's N, right? So if we are bonding the C terminus, right? So let me maybe write this out. So T terminus, ALA, right? LEU, N terminus, right? So if the chemistry is occurring between C and N here, right, that means the one we need to, what's it called, protect, right? So I'll write protect here, N terminus, right? And then here, obviously, we're going to have to protect the C terminus, right? So we could start off by doing that, right? So let's start with ALA. We will write this as you're doing N terminus protection, right? So what is one way? What's one of those groups you guys learn to protect nitrogens, right? So yeah, the Bach group, right? Gigantic, big old group there. It's good for protecting a variety of amines, and I think it works on alcohols too. So if you, excuse me, let me clear my throat so you guys don't get. Ugh, goddamn. Still have like a stuffy nose and thing, but luckily no COVID. I did I went to see family during Thanksgiving in Milwaukee and Chicago, so pretty sure I caught something from someone. But no, it's not COVID. I took a rapid test. So it's just like a sore throat or whatever. Yeah. Okay, so let's hit this with Bach 2O, right? So we could just write it like that. I think it should be fine. I don't think you have to draw out the structure. If you just draw out the reagent, write out the reagent, you should be fine, right? So Bach 2O here is going to protect this. And then we have essentially ALA. It's going to still have this terminus here. And then here we have now NH Bach, right? So we have a Bach protected N group. We are good to go there. Now for LEU, we are same thing. It's an amino acid. What is the R group on LEU? Let's see. It is a isobutyl group. Okay, so in case you wanted the structure, right? Whatever, I'm gonna leave it. You guys can look that up. That's not too important right now. Not a biochemistry class, organic chemistry. Okay, so we want to do a C protection of this, right? What kind of reagents can we use to do that? Yeah, so there's a couple you could choose from, right? But basically, think about it that what you're doing is you're turning the carboxylic acid into an ester, right? That's how you're essentially protecting it, right? Is you're decreasing its reactivity, right? So you could choose anything, right? I know the book does the simple methylation, right? So like you have like H plus, right? So this is just, I guess, basic Fischer esterification, right? So you're gonna esterify this or whatever you want to call it. You know, I would just use ETOH. You could use MEOH. You could probably use, phenol too, I would assume. Actually, phenol, I mean, it's fine, I guess. So he used phenol. Yeah, yeah, I guess it's fine. Yeah, I guess that the issue with the alkyl chain ones would be they'd be more reactive. With the thing with O-phenyl, right? It's okay. So that is a good choice. So you could use PHOH, so phenyl, any of these. It doesn't really matter what you choose. I think, did he teach you that you could use any alcohol here to esterify it, right? I think he'll accept that. You could ask him on Tuesday if he only is like, looking for a certain thing or. So yeah, the Bach 2O is only used to protect what is it? The N terminus, right? So what is it? You have Bach 2O, right? What else? C terminus, right? You could use really H plus in any alcohol, right? It really doesn't matter. I'm just going to use ethyl. It's easy to remember. But you know what? Since you guys use phenol, we'll use phenol too. Why not? Nothing hurts, right? So we have phenol. So now we're going to get OPH, and we still have our NH2 here. So boom, now we have an N-Bach protected ALA, right? We have the O protected here. So now we could force the C terminus of ALA to specifically couple with the the N terminus of ALA. So now we could write it out again here. So ALA, OH, and this is what N-Bach protected. And then underneath it, we could write this. This is C protected. And H2, right? What do we use for coupling? DCC, right? The DCC essentially couples this oxygen here, right? Or I should really say this carbon here, right? To this nitrogen, right? So you get that CN bond formation happening, right? And then I guess technically you have an NH there, right? So now we could say we have ALA bonded to LEU, right? Once again, we have protection on NH, BOC. No, DCC does not protect both. It couples both. So let me write this. This is a coupling agent, right? It's used mostly for CN bond coupling, right? So it's not limited just to peptides, though it's very commonly used here, right? You could use it to form amides too, right? Usually for secondary amides, it's a very good way of like coupling like diethylamine to a carboxylic acid or something like that, or any sort of secondary amines, right? So now we have NBOC protected here, and then we have OPH here. Okay, cool. So now we have the dipeptide. Now what's left is, what was the last one? Glutamate, right? So now we have to bond glutamate here. So we got to use from this dipeptide we have here, are we using the C terminus or the N terminus to bond to glutamate? C terminus, right? So what do we have to do before we can exactly, right? So it's really literally a series of protection, do your coupling, deprotect one side, do your coupling, then deprotect anything remaining, and boom, final product, right? It's just a series of that. So now what we could do here is let's bring this down so that way, like when you guys view this later, it's all gonna be hopefully kind of neat, minus the chicken scratch handwriting. Okay, how do we do deprotection here? Right, so base hydrolyzed, I guess deesterification or whatever you want to call it. So base hydrolysis, right? Not why shouldn't we use acid hydrolysis? Because technically you could do acid hydrolysis to go back to a carboxylic acid, but what's the issue with that? Oh, I forgot something here. It shouldn't be too big of an issue, but actually, no, it's not too big of an issue right now. But one of the general reasons you don't want to do acid hydrolysis is because the amines, the nitrogens that are between the peptides and at the N terminuses, right? They are basic, right? They could get protonated, which could kind of screw up your whole synthesis here, right? So that's why we use base hydrolysis, right? So NaOH, water is your solvent. And then boom, we've opened this back up to its carboxylic acid form, right? So now we could do reactions there. This is still protected, right? OH, right? Now what we want to do next, right, is take glutamate. And we are going to protect what side? N or C here? C, right? We are doing the C bond from the peptide to the N of the glutamate, right? So we could do the same thing again, H plus, and we'll use phenol again. Now we have a C protected glutamate. And we have this side is opened. We could take these two things again. So ALA, LEU, it's still N protected. Damn it. And underneath it, we have glutamate, which is C protected only. This part is open. You can use DCC again to couple them. And then boom, we have our, oops. So we have ALA bonded to LEU, now bonded to glutamate, right? And what we have left is this and okay, and now we just deprotect both things, right? So if you do this, we could just write it as two steps. So one is going to be the NaOH, H2O, and then how do we deprotect the Bach group? Trifluoroacetic acid, right? TFA, right? So what is that? Trifluoroacetic acid. There you go. No, I don't think you have to do a mechanism. I think it's done this way because if you started doing a mechanism, that would take a lot of time, right? Look how many steps this thing is, right? So you just have to do a step. It's consider it as a stepwise synthesis, right? So now after we do our deprotection, C terminus protection of this, we are going to get LEU, GLU, ALA, and then you could OH. Now there's a reason I left this as OH and not that, because if the second step is trifluoroacetic acid, right? So the first step, right, was the base to get rid of this to make this carboxylic acid. And if the second step is trifluoroacetic acid, right, if there's enough present here, right, it's going to also protonate this, right? So that's why, I mean, I don't know if you would lose points if you left it like this, but like just thinking about it logically, if the last thing you treated it with was acid, right, then, only technically the N terminus should be protonated, right? But I think as long as you do, I think the main thing he's looking for is the order of the synthesis and the steps of protection, deprotection, coupling, right? And this is just kind of little extra stuff at the end, but it's why I protonated only the NH3, right? And I didn't deprotonate this because the last thing is trifluoroacetic acid, so it wouldn't make sense for this to be O-, right? But yeah, we'll end on that. Yeah, as I said, once you've done one of these, really, this is all the main difference on your exam will just be the peptides he chooses. All this stuff is the same though, right? Then you just go left to right, or if you want to do right to left, but I think left to right is always easy, right? So you take your things, right? Whatever your leftmost is, you protect the N terminus. Then whatever your next one is, protect the C terminus, couple, deprotect the C terminus, then, keep going forward like that. Then it'll just be if you're going left to right, you only have to do an N protection once actually in this entire thing, right? Then all you could do is keep doing C protections and CD protections and then keep coupling, and then you get your final product. Okay. So yeah, I'll let you guys know if you can do another exam. It's what, the 9th? Yeah, it's 9th. I'll be proctoring that one, so I'm actually gonna be here. I'll try to see. I mean, Wednesday night, most likely. If it would be, maybe Tuesday night. I'll have to let you guys know. Maybe Monday night. I don't know when your final is. I think he made an announcement for it though. Anyways, let me end the recording here though.